Okay, so we're in section 5.9 and we're talking about now approximate integration. So you've learned in the previous sections in chapter 5 techniques for finding antiderivatives, but even with all these wonderful techniques that you've learned, there are still antiderivatives that can, well, there are still problems where you cannot find an antiderivative. Okay, so like for instance, if you look here, this is section 5.9, those two integrals, you cannot evaluate those integrals exactly because you cannot find the antiderivatives. You can't find the exact antiderivatives. Okay, so, and they come up in applications. They come up in applications a lot. A form of the first integral there comes up in statistics. And the second integral, they comment that it arises when a function is determined from a scientific experiment through instrument readings or collected data. So suppose we need to find the definite integrals that you see there in the highlighted gray box. You can't find the antiderivatives, so how are you going to compute those definite integrals? Well, you're going to have to use approximate. Well, you're going to have to use numerical integration or approximate integration, as the book calls it. So remember back when you learned about calculus, when you learned in Calculus 1 about integrals, definite integrals, you learned it was finding the area under a curve, and how many remember inscribing the rectangles? The Riemann sum, yes, that, exactly that, Sandia. So, you know, we have to use some kind of approach where we approximate the area under the curve with adding up areas of rectangles, the Riemann, this book, that's right, this book talks about some different approaches. So like for instance, if we go here to figure 1, okay, they show some different kinds of approximations. So in figure 1, they have a function, that blue function, and they want to approximate the area under that function from the initial point x sub 0 to the end point x sub 4. That's like, you know, a and b. So there they use what's called a left endpoint approximation. Okay, so do you see how the height of every rectangle in figure 1 is determined by the left endpoint of each subinterval? All right, so like for instance, maybe what I can do is I can go to the whiteboard and make that a little just show you here on the whiteboard. So one moment here. Put this in black. X and Y axis. So what I'm doing here is the figure of 1A in the book where they're doing the left endpoint approximation. I'm trying to show you basically how they, you know, how that works. So, you know, there's a function, right? There's a function. And let's say that this is A, this is B, and you're interested in finding the area underneath this function f of x from A to B. Now we know that that area is represented by this definite integral. Okay. And what if we didn't know the antiderivative, Well, we could approximate the area under the function. So what we could do is, for instance, we could take our interval from A to B and divide it into 4 subintervals. So like x sub 0 would be equal to A. Here's x sub 1, here's x sub 2, here's x sub 3, and then B I would call x sub 4. Okay, now naturally, if we wanted a good approximation, we'd have to take more subintervals. But you know, for just teaching purposes, we could go with 4 subintervals. Now we're gonna put some rectangles in here. Okay, so I'm gonna draw a rectangle right here, and maybe I'll put it in red. Okay, there's a rectangle. The rectangle goes from x sub 0 to x sub 1. And the height, here's the height of the rectangle. What's the value? What's the height of that rectangle? That's f of x sub what? F of x.
X sub 0.
That's right, Touch, x sub 0. So you see, you use the left endpoint of this first subinterval going from x sub 0 to x sub 1. You're using the left endpoint to determine the height of that rectangle. If we were to draw now, if we were to look at the next subinterval, okay, it's not related to the tangent, not related to the tangent, but here's the next subinterval, and I'm using this point here to determine the height of that rectangle for this next subinterval. What's the height going to be? F of x sub what? F of x
Sub 1, so x1.
Sub 1. That's right. That's right, Sandia. That's right, Anne. So you see, you're using again the left endpoint. Okay, so we could continue this, right? We could continue this, and we hold on now. We could keep using the left endpoint to determine the heights of the rectangles. And so this would be what's called the left endpoint approximation. That's what you're seeing here, is a left endpoint approximation. Okay, and this is what this is in the recording. I mean, this is going to be in the recording, but this is what they're trying to convey in figure 1A. So let me go back to the ebook now. Let me go back to the ebook. And there is figure 1A, left endpoint approximation. Okay, are you comfortable with that? How they're doing that? Maybe give me a thumbs up if you're if a few of you gave me a thumbs up. That would make me feel comfortable. All right, Sandia's comfortable, and Ange is comfortable. Wonderful, wonderful. Ange is comfortable. And Mario. All right, well, good. Well, now look at B. Now B, they're doing a right endpoint approximation. So now in B, for each subinterval, they're choosing the right endpoint to determine the height of the rectangle. So the right endpoint in each subinterval, they're using the function value at the right endpoint of each subinterval to determine the height of that rectangle. That's called the right endpoint approximation. Now, there are other approximations too. Okay, what if you were to take each subinterval, okay, and use the midpoint of each subinterval and use that to determine the height of the rectangle? So function values of each of the midpoints determine the heights of those rectangles. You see, that's what you have in C there. Okay, that's called a midpoint approximation or the midpoint rule. You see? So those are three ways in which you could approximate the area underneath the curve. Okay, they're Riemann sums in themselves, but you know we're actually giving names to these approximations. And we can even do this. Look here. What if we were to look at every subinterval and inscribe, well, not inscribe, but use a trapezoid for every subinterval. The sides of the trapezoid, the left and right sides, are determined by the function values at the left and right endpoints of the subinterval, and then you just connect a line segment from those values. One moment. Okay, all right, we have these different approaches, and what I'd like to do is I'd like to do one example where we use one of these approaches. So let me go to our files here, and let me bring up an example for you. Okay, so this is a good example. So the function e to the 1 over x power, right? That's e to the 1 over x power. Well, I'm going to give everybody time to write this question down. Okay, I'm going to give everybody time because how many find that writing, it helps them think when they write an example down? It helps them learn. How many are in that category? Okay, Taj is, David, Jan, and Sandhya. All right, so let me give you a little time to copy this example down. Okay. All right. And then we'll talk about it. Okay, give you another couple minutes here. Okay, so now just a comment on notation here. So you see here M sub 10. M sub 10 means midpoint rule. Hold on, that happens sometimes. M sub 10 means midpoint rule with how many subintervals? How many subintervals will we be using?
I guess they're trying to set you off the throne now. Take you out the power out. So they want us to join that
Some background noise here. Ange?
Yeah, 10.
10, that's right, good. Good, that's right. So like in the figure 1 in section 5.9, the little pictures there showed 4 subintervals. Well, okay, and you know, we in each subinterval, you know, we have a rectangle. We can find the area of a rectangle, and then we add up the areas of all those rectangles. But you know, in this case, we're going to use 10 rectangles. So all right, how would we do this? Well, first of all, we recognize that incidentally, we can't get an antiderivative, e to the 1 over x power. There's no antiderivative for that. So we're going to have to use approximate integration. Now, the limits are important because we're starting at 1 and ending at 2. Those are our limits. Okay, so in terms of in terms of like figuring out what our intervals are, we could draw a picture. We could draw a nice picture going from an interval that goes from 1 to 2, and break it up into 10 subintervals. Okay, so let me show you a picture like that. Okay, because really that's really that'll help tremendously. Are there any? And then we'll talk about, is this approximation? We're going to get an approximation. We're going to find out what the midpoint rule approximation is, and then we'll determine if the approximation underestimates or overestimates the true value of that integral there. Are there any questions? Okay. Well, let's look at our solution here. Okay, so I'm going to give you some time to copy, but let me just comment a little bit on this picture here. So you can see I have an interval that goes from 1 to 2 because A was equal to 1 and B was equal to 2. And this section 5.9, of course, will not be on your first exam, but it will be on your next exam. It will be on your second exam. So A equals 1, B equals 2. And so if I take, if I think about delta x, so recall delta, like in the like when you have subintervals, delta x is the length of each subinterval. So I'm going to take my endpoint 2 and my beginning point 1, and I'm going to divide it by 10 because that's the number of subintervals. And so that's going to get me a 10th. And so my first subinterval is going to go from 1 to 1.1. My second subinterval will go from 1 to 1.2. Third subinterval will go from 1.2 to 1.3 because every subinterval has a length of a 10th. Then, of course, I have to pick the midpoints. Well, for the first subinterval that goes from 1 to 1.1, the midpoint is right here, right halfway. Well, that's going to be, that midpoint would be 1.05. And I'm going to let you copy this. The second subinterval is halfway between 1 and 1.2, so that midpoint would be 1.15. The third subinterval is halfway between 1.2 and 1.3, so that midpoint would have to be 1.25, and so forth. Okay. So I find this very helpful to, start this way. Let me let you copy the graph down. And by the way, the x1 bar, x1 bar, x2 bar, x3 bar, that's notation for midpoints. Okay. All right. Let me, and so forth. All right. Let me let you copy this. Please let me know if you have any questions. Okay, well now, what we're going to do here is, this integral, we're trying to estimate it. So, of course, the midpoint rule, m based on 10 subintervals, is an approximation. So that's why I have the little 2 squiggly signs. It's an approximation. And this is the formula. This is the formula here. So I'm taking delta x and I'm multiplying it by the sum of 10 function values, each evaluated at a midpoint. So you might wonder, well, okay, let's see if we can make this formula look a little more intuitive. Think about if I were to distribute the delta x through those brackets on each of the functions. You'd have you know, f of x1 bar times delta x plus f of x2 bar times another delta x plus f of x3 bar times delta x, and it would keep going, right? This would keep going until finally you had f of x10 bar, or f of, yeah, x10 bar times delta x. Okay, so every one of these expressions is a height times a base, which is the area of a rectangle, base times height. So the function value at x1 bar gives the height of the rectangle, and the delta x gives the width of the rectangle. Well, delta x, as you know, is equal to 1/10, because remember, we find the length of each subinterval by taking the b minus a and divide it by the number of subintervals. So that's 1/10. And then, so I think you can see that this midpoint formula here is really just you know, if we distribute the x bar through here, really you're just adding up the areas of 10 rectangles, each of whose height is determined by the midpoint of the subinterval, of the respective subinterval. So now, okay, now we just follow the formula. And okay, well, what would f of 1.05 be? Well, of course, 1.05 is the is right here. That's the midpoint of the first subinterval, 1.05. So the function evaluated at 1.05 would be e to the power 1 over 1.05. The second midpoint for the second subinterval is halfway between 1.1 and 1.2. So it's going to have value 1.15, right? 1.15. So e to the power 1 over 1.15 would be the second function value. And we keep doing this. We keep doing this for all 10 midpoints. We're going to add all those values up and multiply by 0.1, and we're going to get an answer. Okay, and if you do this, like for instance, this you could do on Desmos. You could compute this whole thing, this whole expression on Desmos. This is where Sandia, so WebAssign would tell you approximate your value to 6 decimal places, for instance. This is where you would need a decimal approximation. Usually. Okay. So this is how it would have to be done. Okay, so normally 10 subintervals is the most you would have for a problem, because it does take time. You know, you have to actually get the approximation. That's what WebAssign's going to want. Okay, so you know, you have to actually work it out and get the approximation. Now, I'm not assigning a lot of these kind of problems because it takes time to work it through. Let me let you copy a little bit more. One moment. So what I'm doing, class, is right now I'm going to Desmos, and I'm actually going to compute this, and hopefully I will get the 2.019.101.885. So you try it too. You go to Desmos. I can actually bring Desmos up on the screen, but let me give you just another moment to make sure you have this copied down, and then I'll bring up Desmos. But if you're done copying down, try getting the approximation on Desmos.
Professor?
Yes, Jameson? Question?
Yeah, I had a question. So when you're trying to find delta x, I just wanted to make sure about this for my notes. So the 2 is B, 1 is A.
That's correct.
Is that H for 10?
Oh, this is N.
Okay,
This symbol here is N. N is the number of subintervals.
Right, okay.
Good question. Yep.
Thank you.
All right, you're welcome. Yeah, this is an N class. Okay. All right, so I'm going to keep going here in Desmos. I'm going to try to see. I always like to model things for students. I think it helps them if they see the professor does it. Be careful, that's all. All right, so you're in Desmos too. Trying it in Desmos. All right, let me bring it up here. Let me bring up the Desmos. Okay, so there, give me a thumbs up if Desmos should be showing okay. Who's seeing, is it showing up okay on the screen? It should be. But good, excellent, excellent. So, you know, I went to Desmos just like a student would do. And, you know, I actually typed all of this in, and it's okay, it worked. Worked. Who else did that? Did anybody try that and get the right answer also? Okay, it worked for Jan. Okay, well, great, great. And D'Angelo and Ange. Okay, wonderful, wonderful. So, you know, I think it's actually nice to use Desmos for that. I mean, you can type it on your TI 83 or 84 calculator, but Desmos is good too. Okay, so this is an approximation. Now, it's probably a fairly good approximation because but the question is how good. You know, remember what we're trying to do here. Let me go back to the file. Let me go back here. So we're trying to approximate this integral. And our approximation based on 10 subintervals is 2.019101885. We could ask ourselves, what's the error in the approximation? Well, that's the next step. That's the next step to estimate the error in the approximation. And to estimate the error in the approximation, we are going to need to utilize some formulas. And here I have a formula sheet that I made out that has these numerical integration formulas. We just used the midpoint rule. We just used that formula. But if you were to use, like, for instance, if a problem were to say use the trapezoid rule, well, this is the formula for the trapezoid rule. Okay, and then there's a rule called Simpson's rule too. So what's Simpson's rule? Well, Simpson's rule, I'll show you that. Simpson's rule, if we go to the ebook here, okay, so the trapezoidal rule is when you use trapezoids to help approximate your area under the curve. And you can see those might do a pretty good job because you're drawing a line segment from your two function endpoints there, your two function values. But midpoints actually are pretty good also. Now, if we were to use instead parabolas to approximate the curve under each subinterval. Yes, Sandia's liking that in figure 7. So if you take each subinterval and you pick a left endpoint, a right endpoint, and a midpoint, and pass a parabola through the function values for those 3 points, you get parabolas along that approximate the function along each subinterval. And parabolas can approximate curves better than lines can approximate curves normally. Okay, so Simpson's Simpson's rule is yet another rule that is utilized, and they prove the formula. Oh, thank you, Sandia. I'm glad that helped the Desmos demonstration too. Good, excellent. Well, you know, so what's the formula for Simpson's rule? So they go through a proof. They go through a proof. If you're interested, they show why it's true. Okay, but I think I'm just gonna, you can look at that, but take it on faith that the formula for Simpson's rule is this formula. So anytime we want to approximate an integral, we can utilize one of these formulas. And naturally in the homework, you'll be told what formulas to use. But then you notice in the problem, it said that after we found our approximation for the midpoint rule, it asked, estimate the error in the approximation. So yes, we get an approximation for our integral, but we'd also like to know how good is the approximation. And when we try to answer that question, we need to find what are called error bounds. Okay, we need to find what are called error bounds. So those are formulas as well. And we're going to be this problem that we're working on. We're going to be continuing. I'm very aware of our time. We're going to be continuing this. Thank you. I'm going to be continuing this problem. We've done this part. We've done this part. Okay, but we have two parts left to the problem. We have to estimate the error of our approximation for this midpoint rule. And then we want to know if the approximation is an underestimate or an overestimate. So we're going to be in our next class, on Thursday's class, we're going to be finishing up this problem. Now I'll make one more comment here before you go. One more comment. Let me get into the Blackboard. Okay. One more quick comment here. Thank you for staying a few extra minutes. So hold on here now. Wait. One moment here. Yeah, let me get the student view up, right? Okay, so if you go into the course content, and you click on chapter 5, the integrals there's a section 5.9, okay, under the course content. And there's a link for table of numerical integrals. So if you click on that link, you can get that formula sheet that I made. All right, we'll continue this problem in our Thursday's class. Are there any questions? Okay, give me a thumbs up if you're good. Sandia is good, Tosh is good, and Xavier, excellent. I'll stop the recording then. Thank you, everybody.